Okay. I'll be covering air stress function as it applies to thermoelasticity. So thermal problems that may come up. This is a very short lecture here. I'll give an example. So this will be an example of thermoelasticity, where thermal loads are applied and how Airy stress function has been used to solve problems. In the very first problem I'm going to cover here, I cover a beam that's either free or constrained. On the left side, you will see a free beam, and on the right side, you see a beam that's constrained. This beam is subjected to a thermal load of a temperature that varies only along the y-axis. So meaning, if I look along here, and along here, and along here, and along here, that distribution is the same, doesn't matter where you are, but it varies along the y direction. Is that clear? So again, in my personal view, anytime you're in industry or you're working a homework problem or exam problem, it really pays off to spend 10 to 20 minutes understanding what the problem states. A lot of the errors I see in industry is that people don't have all the facts right, and they start, I call it mouse clicking habit. You're like, okay, I have a computer that's very super powerful and I can create beautiful plots. So I got the CAD model. Let me just start mentioning the whole thing and, doing everything I can to get it right. Produce beautiful plots, put them in PowerPoint, and everybody's like, whoa, that's amazing. The thing comes crashing, and it's because we all got fooled because of your beautiful plots. But the 20, the whole in industry, take about half day. Talk to your colleagues, try to understand the problem. If somebody says this is a temperature distribution that's acting on the problem that you're working on. Okay, thank you so much. Can you explain to me where it comes from, that assumption? Why is the temperature distributing the way you're saying? And then you're not trying to question their expertise, but perhaps they think that you need to analyze it in a certain way that maybe it's not the best way. And a lot of times when you're asking those questions to understand it, the person says, oh, shoot, I think I made a mistake. This boundary condition is not right. So it's actually not, as I stated, it's going to be this way. So you never know. Those conversations can lead to other things. So very important to engage yourself and not just do whatever people say. I mean, you should do the request, but you should try to understand the problem. That's what I meant to say there. So here, the question is to determine the stress distribution for a free beam and a constrained beam. So that's case 1 and case 2. And this is a plane stress problem because it's a thin beam. If it's thin, it's plane stress. Again, we use the biharmonic equation for a thermoelasticity problem is going to look like this, all said and done. That's what it looks like. Alpha is a coefficient of thermal expansion, CTE, coefficient of thermal expansion. E is a modulus of the material, modulus. And T is a temperature distribution. Okay, but that's the equation for thermoelasticity. And this equation also is true, similar to what I had discussed earlier in class. So I'm going to use, to solve this problem, I'm going to use the biharmonic equation, but I'm going to use it in this form instead. And what I did there, start from there. I know what the boundary conditions are. In our scenario, what I expect is that there's no shear stress, because if I heat something up, I don't know why the thing will distort. If it's composites, I can see why it's distorted, but it's not composite. It's a uniform material, isotropic. So I think this makes total sense. I'm also claiming that the stress in this direction, is 0, and I don't expect any variations. That's a good assumption also for this problem. The only stress we're going to assume that varies, that changes, is the one going this way. So then I'll go then and substitute and use my differential equation. So the one here. So clearly, that's 0. I already stated that. So then everything simplifies to this equation. Nothing depends on x. You can see there, nothing depends on x. So that's going to go away. And everything boils down to that. I can now integrate this twice, And if I integrate this twice, I invite you to do that at home. It's very straightforward. Integrating this twice will give you that. You may ask me why. Let me do it quick. So that's equal to 0. Integrated once, I get sigma x plus alpha et partial that respect to y. And that's a constant. Integrated once again, and you get this exact same thing I have there. Okay, so with that said, now you can apply the boundary conditions on either edge. Let's take that offline, given the timeline for today's lecture. I want to be respectful of your time. So on this edge and this edge is free. So apply those two boundary conditions, and those two boundary conditions apply to this right here, provide you C1 and C2. You can actually solve for it. Now, it's in terms of T, because T is temperature, doesn't have to be constant. That temperature can vary. So I can provide a temperature distribution that's not constant. I can give you something that's not constant. And that's why that shows up like that inside that integral. So I invite you to do it at home. Each of these problems, in my opinion, you should try at home, one by one, and gain confidence in your ability to solve it. Every credit in class should be about 2 to 3 hours of work outside of class. It sounds crazy, but that's what the expectation is. So there you go, C1 and C2. Once you solve for C1 and C2, plug it in, and then you get the stress distribution across the beam that's free due to temperature applied across the thing. The actual stress can be found. If you know the actual stress, you can use the constitutive law to get the strains. Yeah, so very straightforward. For the constraint case, I'm not going to even do it because it's actually straightforward. It's fixed on this end and fixed on this end. You're going to use the same approach. The only thing now is that you're going to set the strain in the x direction equal to 0. And when you do that, you'll find that sigma x must be equal to the minus of E alpha delta T. So, by the way, so if you have a beam or bar that you fixed in the x direction and you apply thermal loads, because of that constraint, what does the bar want to do? The bar wants to grow, but it can't. So because of that, the stress will develop into the bar to the point the bar could buckle or it could break, right? So that's why for this, you can actually solve all the problems with the same equations. You apply the boundary conditions, and if you do, you can then get the stress within the beam. But that's how we conclude today's lecture. If you have a question, stop by here in the front or outside. Thank you very much.